We move on to a very important connection between work and energy called the work-energy theorem. The theorem states that the net work done on an object is equal to the change in its kinetic energy. We can derive this quickly. We know that the work done by net force equals net force times displacement. So sum of all the forces give us net force. And we also know from Newton's second law, net force equals ma. So the net work done equals to ma times displacement. From our kinematic equations, we know that this is one of our kinematic equations. Final velocity squared equals to initial velocity squared plus 2a displacement, which gives us acceleration times displacement equals final velocity squared minus initial velocity squared divided by 2. Okay, so we can replace a times displacement at the right hand side. So it will simply give us the net work done equals to 1/2 mv final velocity squared subtract 1/2 mv zero squared, and recall that actually kinetic energy is 1/2 mv squared. So we just proved in this simple scenario, the work done on the object equals to the change of kinetic energy. This is known as the work-energy theorem. The net work done on an object is equal to the change in the object's kinetic energy, where the change in the kinetic energy is due entirely to the object's change in speed. Let's use the work-energy theorem to solve this problem about the Deep Space One probe. Its mass is 474 kilogram and it starts at 275 meters per second. We apply a very, very, very small force, 56 millinewton, over a huge displacement of 2.42 times 10 to the 9 meter. What is final speed? First, the problem we analyze the problem. It gives us the force and displacement. So using that, we can calculate what will be the work done by this force. So the net force we know, and the force is in the same direction as the displacement. The displacement is given, so we can calculate the work, and we know the initial speed, we know the mass, So we can calculate everything in this equation that is given by work-energy theorem, except final velocity, which means we can solve for it if we just calculate everything else. So we can calculate the work. Work is force times displacement, and this is the force. This is the force. This is angle between force and displacement 0, so this gives us 1. And displacement is given by this, equals to final kinetic energy subtract the initial kinetic energy. Final kinetic energy should be calculated by 1/2 mass final velocity, final speed square. Subtract initial kinetic energy given by 1/2 mass initial speed square. So as we said, we compute the equation, we know everything except the final velocity. And now it's just an algebra problem now. We solved the algebra and we find that the final speed should be 805 meters per second. Let's think about satellites in orbit. For a circular orbit, the force of gravity is always perpendicular to satellite's direction of motion. This means gravity does no work, and the satellite's kinetic energy and therefore its speed remain constant. Kinetic energy of the satellite should be a constant. So the question is, we have these two orbits, whether the kinetic energy of the satellite change during the motion. It's quite obvious for the circular orbits, right? The kinetic energy of the satellite doesn't change for this circular orbit. Then how about this elliptical orbit? For an elliptical orbit, the force of gravity is not always perpendicular. For example, in this location, that's direction of displacement, that's direction of force. So sometimes gravity does positive work, sometimes gravity does negative work. Therefore, the kinetic energy of the satellites indeed would be changing over the orbit. Now another quick conceptual question. Which of these has the largest kinetic energy? Leaf, very small mass, very small velocity, cyclonist, cheetah, oil tank. Okay. Well, the oil tank has enormous mass, and the cheetah might run very fast, but those two is not going to compare to the immense mass and the colossal orbital speed of the planet Mars orbiting around the Sun. So the obvious answer is A, Mars orbiting around the Sun. The kinetic energy is the largest. Another conceptual question. How much work is done to a 2 kilogram projectile with initial speed of 5 meters per second? So work equals to change of kinetic energy. Initial kinetic energy is 0. This is 0. So work equals to final kinetic energy. So if we want to find the work, we just need to calculate what's the kinetic energy. Put all the numbers in. Answer is C. The last question for today's lecture. We have an aircraft carrier exert a constant force of 500,000 Newton over a distance of 30 meters on an aircraft with mass 15,000 kilogram. What is the launch speed? So we can calculate what's the work done. and calculate the final speed using this. So we should kick it as 2 times work done would be force times displacement over mass, 2 times 500,000 times 30 divided by 15,000, which roughly gave us 44.72 meters per second. So the answer is